All right, guys, I want to talk a little bit more about the two theorems we talked about yesterday, and we're actually going to prove them today. But I want to talk about, before we get into the proofs of these, the structure of some of our statements, guys, will have phrases in them that are what we may read and say, it doesn't really have a whole lot of use to this theorem. I don't know why I put it. Maybe we think it's negligible, and they just put it in there to be maybe grammatically fancy. Okay. However, I want you guys to understand that mathematicians, in regards to writing things, they want to say the most with the least. Does that make sense? Okay. They want to kind of be lazy with their writing. They don't want to have to be very detailed in their writing. Okay. So if that's going to be the kind of mindset that they take when they write down theorems, is that they're not going to add words in there that aren't important. Does that make sense? Okay. Because if they're not important, they're going to delete them out and make the statement even more concise for you and even shorter for you. Okay. So a lot of people read this theorem, and the other one we talked about yesterday, I'll show you both of them, where it says, in a plane, if a line is perpendicular to one of two parallel lines, then it is perpendicular to the other. In a plane, if a line is perpendicular to one of two parallel lines, then it is perpendicular to the other. If I'm reading that, okay, the bulk of that statement is the if-then statement, right? A lot of times we glaze over the in a plane phrase. If that wasn't important to us, they would not have added that, okay? And we talked about if a theorem is going to be a true fact, then we need to make sure that we write it so that it never gets contradicted. It never has a counterexample out there. And if I just write, if a line is perpendicular to one of two parallel lines, and it is also perpendicular to the other, I have the potential for this occurring. Okay? Would you guys agree? Okay? And I put the slopes in here and all that kind of stuff, but would you agree? And that's actually a little bit harder for me to put the slopes in here. I have to go through another view, but would you guys make the argument that those two red lines are parallel? Okay? Would you make the argument that the black one is perpendicular to one of them? Is it perpendicular to the other? No. Okay? So this would be a counterexample to this phrase if we took the three words in a plane out. Okay? So we need to have this. Oh my God! I closed them before you guys got here. I closed them so we wouldn't cry, and then we cry. Unbelievable! I don't know what you. All right. So the other, we'll get to the fans. The other theorem we talked about yesterday was, it's right here. It says, in a plane, if two lines are perpendicular to the same line, then they're parallel to each other. Again, the if-then statement kind of lays out all the very informative, very useful information, but that phrase, in a plane, is still important because if I negated that, or took that, I don't want to say negated, if I deleted that in a plane phrase, look at this. Would you agree that the purple line or blue line is perpendicular to the black one? Okay, you got that right angle showing up right there, right? They're perpendicular. Would you agree that the red one is perpendicular to the black one? All right, so the last theorem is saying if that's the case, if they're perpendicular to the same line, then they have to be parallel. Are the red one and the purple one parallel? No, what are they? They're skew. Okay? But if I take the words in a plane and keep them in, it's going to force something like that where these two lines and this third one actually end up in the same plane, and now they would indeed be parallel to one another. Does that kind of make sense? Okay. So it negates, or I don't want to say negates, but it deletes out all of these potential counterexamples. Okay. That's something, guys, that throughout, not just, I don't know if it's going to be a huge issue for you in this class, but it becomes a very, very critical thing to think about as you move on through other mathematics. Okay. And that's kind of one of the byproducts of learning geometry at this stage of high school, is because there's going to be several math classes that you take after this. If you get into college, you'll probably have, no matter what your major is, you can always take a bare minimum math class, maybe a stats class or a college algebra class or something like that. A lot of majors are making people take calculus now. But taking a bare minimum math class, you're going to have to be able to read some theorems and statements on your own, and walking through in geometry how we can read those and understand them and interpret them is going to help you at some stage, some juncture in your life, and you have to do it on your own. Does that kind of make sense? So not only try to teach you the math, but teach you how to read the math and interpret it. Okay. All right. So what I want to do today, we're going to do one of these together, and then you're going to spend a little bit of time developing the second one on your own, and then we'll come back together and talk about the second one. But we'll start with this one. Okay. And we're going to prove it, and I want to start from scratch. Okay. I want to go all the way back to the idea that if they ask me, prove theorem 3.9, okay, or this phrase, how do we go about kind of collecting the information that we need to be able to do that? Okay, so I'm going to see if I can type this stuff. Might make it a little bit easier. All right, so our given. You guys remember what your given is when we look at the theorem as a conditional statement? What part of the conditional statement provides your given? The hypothesis. Good. The if part. Okay. So I'm just going to write out two lines are perpendicular to the same line. Okay. So our given, when we go through our proof, is going to be that statement. Okay. Our proof then, if the hypothesis was our given, then our proof is probably our what? Conclusion, the then statement, right? What we're trying to get to, the conjecture we're trying to arrive at, which says they are parallel to each other. Okay. Now, those two statements are really not that great in the way that we've written them. I just kind of cut and pasted out of the theorem. But now we want to rewrite them so that they are in a format that we can actually talk about specifics. Okay? Talk about specific lines and things of that nature. So, two lines are perpendicular to the same line, and it says they are parallel to each other. That's the then. They are parallel to each other. The first thing I think we should probably pay attention to is that the word they, what does that reference back to? The two lines, right? I don't know if that, I don't know if I was paying attention today in English class when we talked about direct objects. Is that direct object? They want to reference back to, I don't know, I'm asking you, okay? But there's something grammatically about they referencing back to the two lines and not back to the same line. Does that make sense? Okay. And we need to understand that so that we can convert the given into something that we can actually use. Okay. So when it says two lines are perpendicular, you get to choose your two lines. What do you want to call your two lines? Use anything that you want. I think the best thing to do is to use just lowercase letters. But use whatever you want. So I'm going to use and I'm going to, I don't know, maybe if you want to write that down right now that way, because I'm going to go back, I'm going to delete some of that and rephrase it and that kind of stuff. It says given two lines. So now I've changed two lines to J and S. Does that make sense? Call it whatever your lines you want to be. Doesn't matter. Okay? They are perpendicular to the same line. Well, it'd be nice to have a name for that same line. What do you want to call that same line? Call it anything you want, guys. I'm going to call it I'm just call it T. Okay? So J and F are perpendicular to the same line, T. Now, if you want to leave it that way, that's fine. But I think it makes more sense to go ahead and do this. Rewrite my given this way. J perpendicular to T and F perpendicular to T. Does that say the exact same thing as the above two given statements? Okay? So it's a process, guys, that we have to walk through to get our if statement written in a manner in which we can talk and discuss about particular objects. Okay? Now, if you use, let's use my initials. If you use A, B, and C, or whatever you wanted to use for your line, it doesn't matter. Okay? Okay, so even, hopefully maybe you guys know, we talked about it yesterday, that it's kind of a pain in the butt with PowerPoint, but we could insert a symbol here. You guys know where to do that at? Insert symbol, there we go. Okay, see the perpendicular symbol here? There it is. All right, so if you want to write it this way, I don't really know if that's the perpendicular symbol that's meant for PowerPoint, but because it kind of puts it at a different level than where it should be. But does that kind of make sense? That's what we're given. All right. Now we want to say they are parallel to each other. Well, what did you guys tell me they was? They was the two lines, right? What did we say they? What did I choose for my two lines? I chose J and F, right? So I'm going to say J is parallel to F. And now that's what we would have to come up with if it was set upon us as a task to just prove this in. They said in front of us, it says, prove in a plane if two lines are perpendicular to the same line and they're parallel to each other. That's what you have to go through and do. You have to decide what you're going to call these things and how to talk about them. And once I write that given in that proof statement, I want to make sure that I haven't written anything that contradicts what the theorem says, right? I want to make sure that I have two lines that are being perpendicular to the same line. So I got J and F, perpendicular both to T. And then I want to make sure that in my get or my proof statement that I do end up with they are parallel to each other. So J and F, the two lines I chose, they are parallel to each other. So I have everything that this statement here says in a concise way so I can start talking about it. Does that make sense? All right. Now, part of my given is also a picture. All right. So we need to draw a picture. Well, the picture should model your given. All right. So I go through this kind of statement by statement. It says J is going to be perpendicular to T. I'm going to create a line, J, and we'll create a line, T. I'm going to create them so that they're perpendicular. I'll put a right angle in there just to remind myself that they are perpendicular. Does that make sense? Now, the way you drew yours might be completely different. Okay, you might have drawn a horizontal J and a vertical T. You might have drawn a horizontal T and a vertical J. It doesn't matter as long as they're perpendicular. Is that okay with everybody? Now, if that's the case, then F also has to be perpendicular to T. Well, could I draw F right here? Would that be perpendicular to T? Can I draw it right here? Can I draw it right here? I've got options now of where to put F. I'm going to put it down here. Okay? Well, we're going to say that F is perpendicular to T. All right? So that's the picture that our given kind of sets up for us. Now we're going to go through and we're trying to prove this. Okay? So again, as we prove these things, guys, obviously you're going to write your given down first. So I'm going to kind of cheat here. Cut, paste. So statement number one is that J is perpendicular to T and F is perpendicular to T. That's my given. Okay. Now, as always, when we have vocabulary words in our given, that's the first thing we want to address. So if I have J perpendicular to T, what does that produce for me? What does perpendicular create? Just in general, if I have two lines that are perpendicular, you know automatically you're getting what? Yeah, you're getting right angles, right? You're getting 90-degree measurements. So I want to talk about some angles up here that are right angles. In my picture, I don't have anything to describe an angle by, right? If I say, guys, look at that blue angle up there that has a right angle marking in it, you would not know how to call that or identify that, right? There's no name for it, okay? So somehow we're going to need a name for that. And I'm just going to put a 1 in there, okay? And to be honest with you guys, I didn't even know that that's the one I should, because isn't this a right angle as well? Based off of what we know about perpendicular? Isn't this one come down here, 5, 6, 7, and 8? If I want to put all 8 of those angles in, that's fine, okay? And we're kind of talking about maybe doing that and making a link between some of those other angles other than 1 and 6 here, okay? I need to tell everybody that I need to be able to describe them. I need to be able to talk about them. So I put those numbers in there. Does that make sense? Okay. Now, what a textbook is going to do is you're going to put them all in, and the author is going to go through the proof and say, okay, I didn't use 7, so let's delete 7 out of the picture. I didn't use 5, let's delete 5 out of the picture. Does that make sense? And then they're going to start you then with just the things that they use, so it gives you a little bit of foresight on what you need to use. Okay. But if we're doing it all by ourselves, all 8 of those angles are fair game. All right? But if J is perpendicular to T, J is perpendicular to T, I'm going to come up here. And I'm going to choose one of those 4 angles to talk about. Let's just choose angle 1 because it's already got the box in it. Okay? What would you know about angle 1? What kind of angle is it? Right angle. Angle 1 is a right angle. The reason for that, how'd you know it was a right angle? Yeah, the lines are perpendicular. And we know that set out in the definition of perpendicular is that there are 2 lines that intersect to give you right angles. So this becomes definition of perpendicular lines. Okay. So that took care of that first vocabulary word that is linking J and T. There's another vocabulary word in a given, right? Turns out it's the same one, but is it linking different components? Yeah, it's linking F and T now, right? F and T. So over here, okay, with that red line in the blue line, I want to talk about one of those angles being a right angle. Okay? Now, kind of thinking, because this is what you got to do when you're doing proof, is think about the tools that we have at our disposal. We're trying to prove lines parallel, right? The only way that we can prove lines parallel is if we show corresponding angles congruent, we show alternate interior angles congruent, we show alternate exterior angles congruent, or we show same side interior angles supplementary. Those 4 things. Talk about in section 3.3. If I've already said angle 1 is a right angle, which of these 4 angles down here on the bottom makes sense for us to talk about as a right angle as well? Angle 6. Why does it make sense to talk about angle 6, Shayla? Okay, because we got the marking in there, but the reason I put that marking, I can put that marking anywhere. I can put it in 5 and put it 7 and 8. Okay, because of what I've already used, angle 1 I've already identified, right? 6 is corresponding to that. Okay, and I know in the back of my mind that we have a theorem that says if I can show corresponding angles congruent, the lines have to be parallel. All right, so I want to see if I can talk about corresponding angles. Maybe it'll get me where I need to be. Maybe it won't. Maybe it'll be a roadblock at some point, and I gotta go try something else. Maybe then 1 and 5 would be better to look at, or 1 and 7, or something like that. Does that make sense? Okay. So now I'm going to type in that angle 6 is a right angle. Okay? If I ever categorize something as a right angle, I've got two options. One is because of the definition of a right angle, which says it's a measurement that has, or an angle has a measurement of 90 degrees. We haven't done that. We're not talking about 90 degrees here. Or it's because I had perpendicular lines. So here again, reason number 3 would be definition of what? Yeah, definition of perpendicular lines. Okay, because I knew that F and T were perpendicular, so it's going to yield me right angle. All right. So as we start writing more and more statements on the left-hand side, we get to a point where we start combining those and create new statements using our kind of our laws of syllogism, laws of detachment, that kind of stuff. Okay. What do we know based on statements 2 and 3 that we can say about angle 1 and angle 6? They're congruent. Okay. Angle 1 is congruent with angle 6. And if you remember, we had a theorem, it was about 2 weeks ago. And if I give every one of you a right angle, can any one of you take your right angle and lay on top of anybody else's right angle? Okay. And that means that any two right angles are what? Congruent. Okay. I've always phrased it as the way I was initially taught, all right angles are congruent. If you want to phrase it as any two right angles are congruent, that's fine. That's the logic of why we say angle 1 is congruent to angle 6. But angle 1 and angle 6, why do we choose those? Because they were in corresponding positions to one another, right? They're in corresponding positions and they're congruent. That's what we're showing. 1 and 6 by our picture in corresponding positions. They're now congruent through that statement number 4. So what's that tell you about your two lines, J and F? They're parallel. Okay. Statement 5 says J is parallel to F. And now my reason will be if two lines are intersected so that corresponding angles are congruent, then the two lines are parallel. Not just with the it's kind of messy there, but so now we know if those two lines are parallel. Sheila? You could. It's probably not a bad idea to do that. To say, like over here in a statement, like maybe, like right there, maybe to come and say 1 and 6 are corresponding angles, and our reason will be definition of corresponding angles. But that's something we can gain from a picture. It's kind of like when we talk about linear pairs and something like that. We can look at a picture and know that they're linear pairs. We look at a picture and know things are vertical. So we don't necessarily have to write that. It would not be wrong to say that. And to be honest with you, I'm of the, and I wasn't this way in high school until I got to college, and actually had a unique job in college that I became extremely detailed in the way that I try to view things. Like if I was doing this on my own, yes, I would put that in. But I'm not going to make you guys do that because it is something we can gain from a picture. But as long as you're putting true statements in there, that's fine. Okay. If you at some point wanted to write in there that 1 and 2 were complementary, it's absolutely true. It's not beneficial to the proof. It doesn't help me move along through the proof, but it is true, so there's nothing wrong with it. Does that make sense? Okay, so I want to, now you don't have to write this down, but I want to go through this again. Control C, let me reduce this. All right, so I want to go, the black one is the one we just did. We're going to leave it alone, okay? But I want to go through and show you maybe some different ways that this can be proven to kind of justify then the argument that just the way you do it is not the way your neighbor has to do it. The way I do it in class might not be the only way that you got to do it, okay? You guys want to move that, one of you guys up there front, want to move that fan so it does blow on you instead of the filing cabinet, you can. But what we got here, guys, is we chose 1 and 6, right? Okay? We chose 1 and 6. But is there anything that says I had to choose 1? Let's choose another angle up there. Let's choose angle 2. Okay? Could I have chosen angle 2 and put 2 right here? Okay? Is 2 going to be a right angle? Yeah, so maybe I put 2 right here instead of 1. Okay? Now, thinking about what we've already done, what would be a good angle to compare with 2? Okay, now, what I want to do, because my goal is to show the black line and the red line parallel. So I want to choose an angle that is made off of or because of the black line, and then an angle that's made off of because of or created because of the red line. So I don't want to choose 2 and 4 and compare those, because it's not going to give me that red line, right? So you said 5? Okay, so 2 and 5 would be corresponding, wouldn't they? So I could have put 5 there, and it changes this to 2, and it changes that to 5, and really the statements and reasons are identical except for those things, right? Does that make sense to everybody? Okay. So that's a different way of doing the proof. It's using different things to talk about. Could I have used, for the same reason I used 1, we used 1 and 6, we did 2 and 5, could we go 3 and 7? They're corresponding as well, and 4 and 8, right? So there in itself, guys, is 4 different ways we could do this proof by changing our choices of those angles. When you see this stuff in, like your homework or whatever, or the end of course exam, if they give you one, that they start you with the picture, that's kind of probably what they'll do right here. They'll give you 1 and 6, okay? And those be the only thing that they provide you, because they know that these other ones that I kind of took out here didn't get used throughout the proof, all right? Or they might start you with 2 and 5, and then obviously those would be the ones that you want to use to kind of work yourself through that proof, okay? Now let's say this. Let's say I did choose 2. My eraser doesn't want to work. And then I chose 7 down here. Can I do that? Are they corresponding? No, they're not corresponding. But they are what to one another? Alternate exterior. Okay? Did we have a theorem that said if 2 parallel lines, if 2 lines are intersected so that alternate exterior angles are congruent, then the lines are parallel? Yeah. So I could use 2 and 7. 2 is still a right angle, so I leave that statement alone. 7 is now a right angle. So now 2 and 7 would be congruent. J would still be parallel to F, but now this thing right here, this phrase where it says corresponding angles, would be rewritten as alternate interior. Oh, exterior, sorry. Good. Exterior. Okay. So it's a different way of doing the proof, right? We changed some of the statements on the left-hand side, and now we need to change the reason on the right-hand side. Okay? But if you did it that way, and your neighbor did it the way that we did it first, in the black up there, you're both right. All right? Could I do, could 2 be here and 7 be there? What kind of angles were those? So this changes to alternate interior. All right? What if 2 was there and 7 was there? Those are same side interior, but when I talk about same side interior, what's the relationship the same side interior angles have to have between one another so the lines become parallel? That'd be supplementary, right? So that, if I'm going to use that relationship, which is fine, you can, it's going to be a little bit more involved, okay? What we would have to do is say, at this point, even though I say angle 2 and angle 7 are congruent here, and I can still write that if I want to. There's nothing wrong with saying that, but it might allow us to say here that angle 2 and angle 7, there's several different ways of doing this or justifying this. Let's write it this way. Let's go measure of angle 2 equals 90 degrees, right? Measure of angle 7 equals 90 degrees. You guys agree with that? That's the definition of right angles, right? Would you then kind of make the argument, and we could do the algebra if we wanted to. I don't think we need to do the algebra here. Would you guys agree that angle 2 and angle 7 are now supplementary? Okay, and I think anybody that's reading your work would be able to know, well, 2 and 7, that's 90, add to 180, so they're supplementary, right? If you want to put the algebra in here and carry a couple more steps, you could. But that would be definition of supplementary angles, right? I don't know why it's doing that. Okay. And now, could I say J is parallel to F? But my reason being, if two lines are intersected so that same side interior angles are supplementary, then the lines are parallel. Does that make sense to everyone? Okay. We have options, and that's kind of what I think you guys collectively, I don't say everybody, but a lot of people don't like that because you've been trained in Algebra 1 one way, only one way to do it. Okay. You've been trained in 7th grade, 8th grade, one way, only one way to do it. There's not. Okay. And the more math you gain, the more understanding you gain, you start to open those doors. Okay. Is that all right? All right, now I want you guys to get practice at this. So I want you to take 4 or 5 minutes. You can work with some people around you. I don't want you getting up and changing desks and all kind of stuff. But kind of collaborate on writing a given and a proof and a picture just like we did for that first theorem, but using this one here. Okay? So give you about 4 or 5 minutes to do that. You don't have to start proving it. I just want you to write the given and write the proof statement using specifics. Okay? Here. All right, so if we've got that theorem, in a plane, if a line is perpendicular to one of 2 parallel lines, excuse me, then it is also perpendicular to the other. So I took the given out, took the if out, wrote it as my given, took the then out, wrote it as my proof, right? Okay. The given says if a line is perpendicular to one of 2 parallel lines. There's 2 facts going on here. You should have 2 lines that are parallel. So you need to talk about 2 lines that are parallel. That make sense? Okay. I think I chose B and C being my lines that are parallel. B and C right here are lines that are parallel. If I write A perpendicular to B, does that create the first part that says a line, our line A, is perpendicular to one of the 2 parallel lines? Does that make sense, everyone? All right. So that's kind of the structure that I'm looking for there. And it says then it is also, so it is referring back to that line, which would have been our A, right? Does that make sense? Okay, so then it is also perpendicular to the other. The other would be the other parallel line. So it would be C. So we're going to say A is going to be perpendicular to C. That's what we're looking for. Okay? Now, here's my argument to you. Why are we good at that? How do we get better at that? We pay attention in English class. Okay? We learn how grammar works. We learn how direct objects and adjectives and verbs and all that kind of stuff operate. And then it's easier to decipher the stuff that we do in English. Okay? The things that we do in math. English is helping there. Does that make sense? Okay? So now if we wanted to draw a picture, our picture of this thing has to mimic the given, right? So I need two lines that are perpendicular. I don't care what they look like. I'm just going to make sure that they're perpendicular. So my picture maybe is going to look like, maybe that's A, and then maybe that would be B. Are they perpendicular? Do they look perpendicular? Okay. So that is that criteria. But now B has to be parallel to C. So I'm going to put a C in here, line C, and I'm just going to put it in so it's parallel to the blue one. Doesn't matter where I put it in, as long as I hold the characteristics of being parallel. Now we want to prove that A is also perpendicular to C. So what would I need to show? If I want to show this red one is perpendicular to this black one, what do I need up here? I mean, what types of things? What is described for us and provided for us in the vocabulary word or the definition of perpendicular? Okay, so I need that little square. What's that little square represent? A right angle. So I need to talk about one of these spots as becoming a right angle. Okay, if I can do that, then the lines are going to be perpendicular. Is that all right, everybody? So let's see if we can kind of walk through that real quick. I'm going to write a given. A perpendicular B, B parallel to C. Two vocabulary words there. Perpendicular. A perpendicular to B. So we're talking about the blue line down here. One of those four angles is going to be needed to talk about as a right angle. Doesn't matter which one. Okay? Whichever one you want to use here, you have to write it as a right angle. I'm going to use angle 1. So the angle 1 is a right angle. How do I know angle 1 is a right angle? Say again? It's marked, but how do I know it's marked? Because sometimes it might not be. Because it's perpendicular. So the definition of perpendicular line tells me that that is indeed a right angle. Okay. Now the other vocabulary word. The other vocabulary word is right here. Parallel. If I look in my glossary for the definition of parallel, it's going to say it's two lines, two coplanar lines that never intersect. That doesn't really get me anything. Okay? Parallel is one of those vocabulary words that really doesn't get you a whole lot based off its definition. But it gets you an immense amount of information based off of theorems that we have and postulates. We know if you have parallel lines, what types of angles should be congruent? Give me a name of angles that should be congruent. Corresponding, what's another name? Alternate exterior, what's another one? Alternate interior. Okay, those should all be congruent, right? Okay? So if I've got that at my disposal, let's look up there all those question marks, and let's choose one of those question marks. Let's put a number in for one of those that is either corresponding, alternate interior, or alternate exterior with the angle 1 that we've already used. Okay? So I'm just going to go, because maybe be a little bit different than last. Let's put 3 right there, angle 3. Would you guys say that angle 3 should be congruent with angle 1? Because we know through that, those two lines are parallel, right? So what kind of angles are 3 and 1? Alternate interior. So this is the alternate interior angles theorem. Okay, yeah? Where? Oh. So that's that 3. That's the one for the red 3. Okay. So those are alternate interior, right? Okay. Alternate interior. So now here, and we don't really. There probably could be more steps to this if we're going to try to be extremely detailed. But think about this. Angle 1 is a right angle. Angle 3 is congruent to angle 1. What's angle 3 got to be? So I can write angle 3 is a right angle. Okay. Now I'm going to use substitution for that reason. Just think about this. Basically, I've rewritten that phrase there, right? So I took out angle 1 and replaced it with what it was equal to, or what it was congruent to. So I'm going to use substitution. And If angle 3 is a right angle, what is in the relationship between the black line A and the red line C? Yeah, A is perpendicular to C, because when you have perpendicular lines, you get right angles, right? But when you have right angles, you must have what to create those? Perpendicular lines. And that's the definition of perpendicular line. Okay? I think, guys, it's really important for us to be able to recognize the usage of these theorems, okay? The usage of previous theorems to help us prove current theorems. We're continuing to use these next couple days. My thought is, I told you yesterday, I was thinking of a quiz later this week.